Alrighty. I think this is the last day of the month. No, I think May goes third one. Okay, second last day. Snakes and ladders. I guess I probably did this before in the DSA course, but I guess let's see how I do try and recreate something I previously did. You're given an n by n integer matrix board where the cells are labeled from 1 to n squared in a I'm not sure what this word is. Ostrophodon style. I think it just means it goes back and forth, back and forth. Starting with bottom left of the board at n minus 1, 0, and alternate each row. You start on a square 1 of the board, and each move starting from square current do the following. Choose a destination square next with the labeled in current in the range current plus 1 min of current plus 6n squared. This choice simulates the result of a standard 6-side die roll. There are always at most 6 destinations regardless of the size of the size of the board. Choose the destination square. Okay, so 1 or 6 more than it up to the last square of the board. And this starting square is 1, so let's go to n squared. Okay. If next has a snake or ladder, you must move to the destination of that snake or ladder. Otherwise you move to the next game ends and reach n squared. Board at row R and C is a snake or ladder. If the board at R and C doesn't equal -1, so I guess the board is mostly -1s. The destination of the snake or ladder is board RC. Squares 1 to n squared are not the starting points of any snake or ladder. Okay. Note that you only take a snake or ladder at most once per die roll. The destination to a snake or ladder is part of another snake or ladder. You do not follow the subsequent snake or ladder. And so the board is -1, 4, -1, 3. So -1 here should be the start. On your first move, your destination is square 2. Square 2 is going to be the square, which is 3. Follow the ladder to square 3, and you do not follow the subsequent ladder to 4. Interesting. So destination is square 2, which is this. You follow the ladder to square 3 because this thing notes. So 3 goes to this one, and then because this one also goes to a different square, you don't go to it because or the end of the snake or ladder. And you're supposed to return the number of tiles, number of moves. To return the least number dice roll. Here the least number dice roll would be like 1 die roll to go to 3, which goes to 4, and then a die roll to go to the end, so like 2 die roll. Alright, so this one, like, 1, and then 2, and then 3. Oh, whoops, this is going to 15, you can't go backwards. So 1 to 2, which goes back here to 3, and then to 4. Okay, alright. Let's see if I can't figure this out without knowing which course this was that I did. I think this is probably maybe dynamic programming. For each square you're trying to determine what the least amount is to get to that square, and then you can extend it farther and farther out. So I'm going to try dynamic programming here. For each square, determine the least amount of rolls to get to that square. Okay, so let's say I know there's currently a 2D board, but it might make sense to make it into a singular array so that it's easier to index. Do you even need to worry? Do you even need to worry about? Yeah, it just create a single array for it. Okay, so say create 1D array equivalent for 2D board. So I can say for every row in board, actually, let's create a variable n is equal to length of board, which is the number of rows, which is one dimension of it. And then for index in range, let's see, index in range of n squared. Index for every row. For every row in range. So I want to go backwards and forwards. How best to do that? Every index in range n squared. So it starts off going forwards the last row. So we start off with like this row right here. So this is for every row index in range. So the row index is going to go backwards. So it should go n minus 1 negative to 0 to negative 1. Because you do need to go to 0. So and it doesn't include negative 1. So I think that's right. And then for a particular row, you want to go backwards and forwards. So if the row index is, say, let's say backwards. Actually, let's say forwards is equal to true. If true forwards, then you want to go for every column index in range. For every column in range. So you want to increment the column index. So it's going to be in range of n. Say array is equal to that. And we'll say array dot append the board at this row index, column index. And I guess I could just call this row and column. Otherwise, you go for every column in range of n minus 1, negative 1, array dot append board of this row and column. There's a better way of doing this. I guess it's fine. It's not elegant, but it's fine. Turn off the array. I guess I deleted a colon. Alright, so let's see if this compares to what I expect. So -1, 3, -1, -1, that's correct. So the last row should be the first set, and then this thing should be backwards, which I can't tell. And then this thing should be forwards, which I think that is correct. Okay, so let's go ahead and just do one small test case on case 2. So it's going backwards here, forwards here, and then backwards here. Let's say this is like, say this is 4. So it'd be -3, 4, 1. -3, 4, -1. -1, 3. This is incorrect. It should be 4, -1. Oh, I never toggled the backwards and forwards. Forwards equals is the negation of forwards. I think that's how you toggle it. -1, 3. Oh, oops. It's equal to not forwards. There we go. Okay. Do this. Python toggle is boolean variable. Yeah. This XOR with 1. Okay, -1, 3, 4, -1. Okay, that's right. Okay, so now that I have a one-dimensional array, I can not worry about the exact row and column deal. So each index in the array refers to another index in the array. So, or -1. So I can say that I'm going to create a dynamic matrix, DP matrix for each. Is this going to be a matrix, or is this going to be a single array? DP dynamic programming array for each index. Determine the lowest number of roles to get to that index using everything up to that index. So I can say here that for every index, actually, so DP array is going to be what should I initially set it to? I should probably initially set it to something really high because then it's going to be minimized each time I see it. So I'll set it to, at worst case, it'd be n squared. N squared times the number of times n squared. Okay. Go ahead and just verify that that is what I think it should be. So it'd be like 4, 4, 4, 4. Okay. and I initially will, generally when you do these, you always kind of set your initial value to be something that's not that. So it takes 0 rolls to get to the starting square. And then for every index after that, so actually this should be n squared plus 1. So it's like n squared plus 1. The number of rolls to get to n squared takes you 0 rolls to get. Maybe it is actually just n squared. So for every index in range of n plus 1, no, in range of n squared, Actually, I don't want to calculate n squared each time, so I'm going to go create say total, which is n squared. And so BP is going to be total, which is going to be, I'm setting it to total because it's like an arbitrarily high amount that it's always going to be less than the number of times that the number of rolls that you need to use to get to any square should be at least, or at most, like the square number, because then that means like you're using ones to get to every step. Otherwise you could use like infinite, like float infinite. So for every index in range, actually I think this might be, yeah, I guess you do start with 0. So the index is going to be starting with 0, and then you'd go for every square from 1 through 6 from here. For every square from 1 to 6. Actually, let's say index is in range total. Let's say the number of rolls that we currently have is dp of this index. So you got 0 to get to 0. And then for every die roll in range of 6, of 1 to 7, which is 6 more, if the die roll plus the index is greater than the total, greater than or equal to, or greater than? I think it should be greater than or equal to. So square 1 is actually index 0, last square that's actually index n-1. So it can't be equal to, so then just break, because we can't do that. Otherwise, you can say that to get to, actually let's say that next square is equal to die plus index, and if the next square is greater than equal to total, then break. Now it could be a snake or a ladder, so you need to determine based on the board what the actual thing is. You determine based on the board what the actual thing is. So if I think about how the board is set up, so initially all these squares have like 36 as the initial starting number of die rolls to get to each square. And then I make this 0, so it takes 0 rolls to get to this thing. Now when I update it and say that it takes like 1 roll to get to this thing, I want to say that it takes one roll to get to 15. But does it take one roll to get to 2? Or does it still take like an impossible number of rolls to get to 2? I guess you can always choose. You always have to go down this ladder or go down the snake. So it's not possible for you to do one die roll to get to 2. So when you do 2, 2 is going to be awkward because it's going to start with n squared. It's going to start with kind of an impossible amount of things. I guess that's fine because it's still going to be bigger than the other stuff. I guess maybe I can say, like, if the number of die rolls to get to this thing is n squared, then just skip it. If rolls is equal to the total, then it's really not possible to go here. There might be another way to get back to this thing using kind of reverse, but moving forwards is not really there. I think that's correct. I'm not quite sure. Alright, so the next square, if the next square is bigger than that, then if the next square is out of bounds, it go out of bounds. So if the next square is based on the board, if the board at the next square is not equal to -1, next square is whatever the board says it's going to be. So go down that the board, and then I can say dp of the next square is the minimum of dp of the next square versus one more roll from the current number of rolls. And then I think that might be it. List indices must be integers or size accomplished. Minimum of dp of the next square. List indices must be integers. So somehow this thing's not integer. dp of the next square. Is the next square not integer? Or at the next square. Okay, let's go ahead and just print next square here. Next square is actually it's actually a array. Oh, whoops! I meant to go with my 1D board rather than 2D board. So array at the next square. If the array at the next square is not -1, go down the path. Okay. It's probably going to take too much. List out of bounds. List out of bounds. So array the next square not equal to -1. If the next square is greater than its total. Okay, then go ahead and next square before it goes out of bounds for us. So here saying that the next square is 6, and array 6 is -1. let's go count the array here. Array has 0, 1, 2, 3, 4, 5. Is the array the wrong size? Looks like the array does go through it correctly. Actually, the array, no, that's not correct at all. This is just like the first row. The row in range n minus 1, negative 1 to negative 1. Row index. If it's forwards, then do the forward columns. Otherwise, do the backwards of columns. Array append row column. Yeah, why does it not do the other rows? So let's go ahead and print the forwards equals nonce. So it's only doing one iteration of the thing. If forwards, else n minus 1 to negative n minus 1, negative 1, negative 1 should be right. Okay, so let's go ahead and do print the row index and the forwards. 5 true. So forwards equals not forwards, so we should say 5 true and then false. Okay, then next time it should be 4. Should it not be? N is 6. So start with 6 minus 1, which is 5. Decrementing downwards. So it'd be 5 and 4, I think. It's really screwing this up. Yes, I am really screwing this up. Forwards becomes false. And then it should make the row be 1 less. Oof, what is going on? The row always goes highest to lowest, but it's not even going through the second iteration. Crazy. This is how you make a decrementing port. Okay, 6, 5, 4, 3, 2, 1. Okay. Second time it does it, it doesn't do this loop. Loop 5, that prints out false, and then it doesn't do loop 4. for row range. There's a oh lord, I tabbed it correctly. Shit. That is embarrassing. Okay, there we go. So it was breaking because it was tabbing and I tried to do the second version. Okay. I was pretty sure that initial part was correct at some point. Okay, so doesn't go out of so it still goes out of bounds here. So next square is 2. So it goes -1. So it goes 1. So what's the printing here? Next square is 1. Oh, this thing, yeah, this thing can't be 4. That's probably just a bad test case. Okay, there we go. So it takes 1 roll to get to. It should take 1 roll for it to get to. It should take 1 roll for it to get to 3. 0, 1. Okay, next square is actually what is the correct indexing? So if next square said 3, then the index there should actually be 2. I wonder if I should. It's not -1, then array at next square -1. So it go indexing would be 0 through n-1 rather than 1 through n. Okay, so it should take 0 rolls to get to the start. And then 1 roll should get to. Okay, yeah, this is correct. It should be 1 at the very end. And then this one should be 4. Oof. Okay, so I don't think I need the next square deal here. So they start and whatever the start index is. So starting at 0, it's a bunch of 1s if you roll 1, 2, 3, 4, 5, 6. But since if you roll 1, then you go up the ladder to this spot 15. Yeah, actually, because you can't do it in order, right? Because if you go from here up to here, then the next thing that you need to process are these ones and this one. Because this one is going to lead you to things that are 2s. You really don't want to process this because maybe there's like, maybe something goes here and it goes back to here. Interesting. So you need to order the processing. And if you don't order the processing, then it doesn't work out. Maybe it still works out. Last thing there is 4. So normally this is going to return the number of rolls to get to the last one. I don't think this is going to work for the non-test cases. So I can easily imagine that you need to do a different order processing. But let's see how far this thing works. Okay, there. So this looks like what's going on here. So we print out the symbol. So this one goes to, everything goes back to 1. 1 being the starting square. Huh. My output was 9 and this one was not possible. Oh, output 9 is just like, that's an impossible output. I can say here that it was not possible then if dp of -1 equals n squared, return -1, else return dp of that last one. This is probably another bug, but let's see if it works past this test case. That was most of the test cases actually. Okay, so let's see where this one goes off the rails. So the answer here was 3. Okay. See if I can figure out what the correct play was. So it's a 6, no, it's a 7 by 7, so 49. And so there was a 3-way to get there. So this is, let's go and graph the array in 1 dimension. So you can go 1 to 36, and then, okay, yeah, in 1 dimension doesn't really work. For every index in range of total, print out the index and array at that index. So 1 you can go to 36, and at 36 you can go down to 2. Okay, so that's probably not the way. I saw there was a skip to 49, so if you can get to 34. So if we can get to 34, I wonder if I should be doing this backwards or forwards, actually. Yeah, probably the same. So 34. So are there any numbers close to 34? So if I can get to, I guess there's maybe other possibilities too. 35 is here. So maybe 0 goes to 7, which goes to 11. So that's 2 rolls. 11 goes to 34. 34 goes to, so see, 1 rolls gets to 7. 2 rolls gets to 35, which is 34 here. 3 rolls gets you to 31. And then 4 roll gets you to, yes, it's too many. Gets you to, what other number works here? 1 gets you to, I guess if you get to 46 is also fine. Then how do you get to 46? With 36, okay, actually, so you go 0 to 1, that gets you to 36, which is this 35. So that's 1. And then 2 would get you to, am I reading this wrong? 36 means index 35. So you're there after 1, 2, 3. No, you can't add 12 to get to 30, to get to 49. So 2 would be, kind of want to go backwards so they can somehow get to 34. Always roll so that you're moving forward. Unless I'm creating my array. So the first thing, 0 through 7 are those. And the next thing is it going backwards? This thing is going backwards. So negative 139. So that seems right. This one goes forward, starting at 6. Starting at 42. Backwards, forwards, backwards. So what's going on here? Forwards, backwards, forwards, backwards, forwards, backwards, forwards. Yeah, that looks fine. So 0 goes to what then? 0 goes to, this can be done in three moves. Only 49 is here, so it's 34. go past 34, then you have to go before 34. 0 goes to 1, which skips 35. 35 goes to 36, 37, 38, 39. None of these is correct. 1, 2, 3, 4, 5, 6. Unless you can do something that is before 34. Like getting 3 numbers. So even 46 goes to 48. 48 is this one. Ooh. 6 goes to 5, that doesn't work. 8 goes to 39, which is 38. I'd be interested to see what the actual if this problem was actually listing the shortest path array rather than the number of the counts of the path. That'd be a lot more helpful for interpreting when I get it wrong. Say the B. 0 goes to 0 goes to 6. 36 element is actually this spot. Then you kind of want to get there again so you can go backwards to 32. Spot 36 is index 35. So 1, oh, hold on. So 1 gets here, 2 goes here, and then 3 goes to there. Okay. Yeah. Yeah, so this was the same issue that I was thinking was the issue. It was like, I can't process it in order. I have to process it from the smallest steps to the largest steps. So maybe I need a heap so that I always process the smallest thing. Or maybe I need a queue. Maybe I need a queue. I always want to process the things that are after. Yeah, I think maybe it's a queue. So the queue starts with maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, queue starts with 0, and then while there are nodes in the queue, so the index is what is top of the queue, and roles is TP of this index. And then I need to also say that when I've seen this index, maybe. Scene. I don't know if this is necessary. Scene is a set. X is and everything else after basically is the same. Rows equals the total. Maybe in a spot where it's impossible. Then for every die roll, check. Then after you do the check, you need to append this next square to the queue. I think maybe you actually don't need the minimum method. Deck square. BP square is first queue always has the smallest number of rolls. First roll, it adds to the queue everything that is one away from that. And then when it processes those things, it puts onto the queue everything that's 2 away from that. So it should never really I don't know if this needs to be minimum, but it definitely doesn't hurt to be minimum. Or isn't incorrect to be minimum. Okay, so let's try that. As test cases, what are the test cases that does wrong? I'm sure there are plenty of test cases that does wrong. Oh, or maybe not. Okay. It's pretty darn slow, it looks like, but it works. So we create a 1D array. Creating the 1D array is fine. Maybe that's not strictly necessary. It helps determine what the position is. I guess maybe you can have a function that returns the row and column based on the index. Then you just need a bunch of translations everywhere. I'm not sure how much slower this dimensionalizing the 2D array is. But let's see if it's the depth that I can improve here. So if I have my doublet queue that starts with 0, I pop, I see if it's already done. If it's already done, then skip it. See what the roll total is. Roll total is impossible. I don't know if this is necessary, this statement. If the rolls equals total, because it doesn't go through the array in order anymore. Or it went through it in order, it went to impossible squares. So I think this might be skippable. And for every die roll to 7, didn't change it. For every die roll 1 to 7, we check to see if it's in bounds. We check to see if it is, it moves to another square. And I think, okay, I think this doesn't need to be a minimum. I think it needs to be dp of next square is equal to 1 plus rolls. Because it processes it in order of like least to highest, so it should always be, okay, maybe I'm wrong then. Is there a way that it's processing that it's not? I think the other thing is I can definitely shortcut if the index is the last index, then it can just be ending it. If the index equals total total mass 1, then I should just be able to return dp of this index immediately. I think that's fine. So immediately when it sees the ending, it can stop. That was an improvement for sure. Thank you. Let's maybe say here if it's not oriented C, yeah, I'm good with this. Not very optimized, but it is what it is. This if statement can be return -1 if dp dp of -1 is equal to total, else return -1 if it's not possible, otherwise return the last entry 1D matrix. I'll have to ponder what I could have done better here. I think this is good. As is good enough. Getting rid of some of this comment stuff. So not my best effort, but summary is going to create a dimensional array equivalent for the board. This is like index, column index increasing slash decreasing, column index alternating between increasing and decreasing, or while row index is decreasing during the appending loops to create the array. So that was this funky thing here. For every row, starting with the last row towards the first row because the last row is the starting thing. And then for every column index, incrementing if it's forward row versus decrementing if it's a backwards row, and alternate when not it's the forwards backwards row. Then second to that is then process the spots in the array using a queue. Where starts with spot 0 and adds to the queue any spots that are one roll or one. So this thing for every die roll 1 through 7, check the next square with some checks for bounds, and if next square is shortcutted via a snake or ladder to a different square of the board. Also check that the number of rolls to get to the next square is minimized if set to the current rolls plus 1. So you have your DP matrix or DP array, which is initially some high amount of rolls for every square. You say that your initial square has 0 rolls to get to, and then every time you look at a particular index, you see how many rolls it takes to get to that index. You see what the possible spots that are one roll away, and you see if 1 roll away plus 1 plus the number of rolls is smaller than the current number of ways to get to that spot. If so, then you minimize it. Actually, now that I think about it, I think if next square is greater than 2 equal to all break, if next square is in scene, I think you can continue. I think that's why it is sometimes. So if you were seen, that means you processed it and have a smaller number of rolls. Actually, it should be after determining what the next square is. Yeah. Otherwise, you should be able to say that dp next square is equal to 1 plus rolls. That's right. That is correct. Okay. Theory false. Why did that theory come incorrect? Time complexity is going to be O of n to make 1D array equivalent. Actually, so n is the O of s, where s equals number of squares, which equals n times n squared. To go through each element in board to make 1D array, and also to process each spot once in the DP. And space complexity, this is going to be O of s to make the 1D array. And I think there was another way, like I could, there was definitely a way to make 1D array and to 1D array board equivalent, and to fill 1D DP array. Yeah. Way to do it without creating this 1D array equivalent, but I mean, I don't think it saves that much space.